linearized swimming equation, and we saw two types of response. The first one was the unforced response or zero input response, right? Why zero input? Because in this case there was no input or forcing function, and we started with the initial conditions of state variables. We had two state variables, del delta and del omega. So at least one should be zero, and we assume that this is the initial condition of this. At least one should be zero, right? And we assume that this del delta of zero is zero, non-zero, and this is actually zero, right? We assume this, that our initial value of del delta was zero, non-zero, and we assume this del delta as zero. That means from this slide, this was assumed as non-zero, and this was assumed as zero, right? That's why after this line there was no del omega of zero term here, but we have the del delta of zero, because this is a non-zero quantity. So this was our zero input response for delta of t and omega of t. Then the second type of response was the zero state response. This is the forced response. In this case, we had our forcing function, right? And the forcing function was actually come in terms of the deviation in the mechanical power unit, right? Del P. This is our forcing function, and this is called the zero state response, because in this case the initial condition for the two state variables del delta and del omega of zero, we assume these two as zero. Okay? So we assumed this both as zero. That's why this is called the zero state response. So today we will solve example 11.2 and 11.3. Before that, let's look deeper into this equation del delta of t. Okay, that is this is our del delta of t. Actually, this solution is called the analytical solution. This is an analytical solution of del delta of t, or the exact solution. Okay, this is not the numerical one. Can you differentiate between the analytical and numerical solution? What is the difference actually? Actually, the numerical solution don't give you the exact value. It gives us the approximate value, right? Can you recall from your numerical method course in the 5th semester that you learned? So you saw that after some iterations, you just can get close to the exact value, but you are not getting exact value, right? That is the approximated values. But for the analytical solutions, this is actually the complete solution, or the exact solution. Okay? That means if you put all the values here, you will get the exact value of this del delta. There is no approximation like here. Now, here to find this del delta of t, first we need to know the del delta of 0, the initial value of del delta. So this will be given in the question paper or in the problem statement. Okay. Then we need the omega n, that is the natural frequency of oscillation. We need omega d, the damped frequency of oscillation, and also we need the zeta value, that is the damping ratio. And this t will be variable because we want to draw the del delta curve with respect to the t, right? So this t will be variable. Now let's consider the first case. Let's say in this case we do not have any damping. So damping t is 0. That means we are not considering any damping effect. If t is 0, what will be the value of zeta? Can you just go back to the zeta and t relation? This is the zeta formula. This is the zeta, right? T by, if t is 0, zeta will be 0, right? So in this case, we are considering that our t is 0, so zeta will also be 0. Now, what will be the value of omega t? In this case, we know omega t is omega n over 1 minus zeta square, right? If this zeta is 0, we will get omega t as simply omega n, right? Because now our damped frequency of oscillation and natural frequency will be the value of theta here? What is this theta? This theta is the theta from this triangle, right? You need to remember this triangle, okay? And you will find the theta by applying this cos inverse zeta formula, right? Do not confuse this theta with the power factor angle. This is not the power factor angle, right? We were in this line, and from this line we took help of this triangle, and we replaced this root over 1 minus zeta square with sin theta and zeta with cos theta. Okay, but you can simply use this line. But if you use this line, you need to remember the theta. That will be the cos inverse zeta. Okay. So if your zeta is 0, so theta will be cos inverse of 0, right? That will be simply 90 degree or pi by 2. Okay. Now let's put all these values here to find the delta of t for this case, or for t equals to 0. So you will get some value here. It will be here, right? So it will be simply delta of 0. Then this term, e to the power minus zeta omega nt. What will be this term? It will be simply zeta is 0. So e to the power 0 means you will get 1, right? Then this term root over 1 minus zeta square. This zeta is also 0. So this is 1. Then here sin this omega t, we can replace it with omega n. Sin omega n t plus theta is pi by 2. So what will be the value, or what will be the result? Sin omega n t plus pi by 2. It will be cosine omega n t, right? This will be the formula for delta of t for this case, where our damping d equals to 0. Okay. Now, can we plot this thing with respect to time? Let's say this is our delta of t. So it is the cosine term, right? So that means it will start from here. It will go like this. Okay. And this value, what will be the amplitude? It will be simply delta of 0, right? Because you will get the maximum value for cos as 1. So 1 multiplied by this will be your delta of 0. Similarly, this will be your minus delta of 0. Okay, and this will be your sine term, the cosine term. Okay. Now, by looking at this wave shape, can you comment on the stability status of this system? This type of system is exactly marginally stable, right? Because it is swinging between these two fixed values, right? Now let's go back to this table that we discussed. This table, okay? This is case number 2, where our t is 0. If t is 0, zeta is also 0. At that time we got two roots aligned with the y-axis, and this is the marginal stability, right? And we said that the delta velocity response will be like this. Our delta will be swinging between these two fixed values. Let's say this is 72, let's say this is 51. So over the time, the delta will either decay or grow. Okay. And here also, this is for the Laplace domain, right? For the S domain. And here this is the time domain, but we are getting the same conclusion here. Now can you relate this thing in the previous table? Do you have any confusion here? No, right? Now, so this is del delta of t. From this, you can also draw the shape of delta of t. How? You have to just add an initial value with this del delta of t, right? This will be a fixed value. Okay. So if you add this with this solution, maybe this solution will be shifted in the upward side, right? That will be the case. Then you will see that you will get this type of curve, that your curve is delta is swinging between, let's say, two fixed values like 51 and 70, like this. Okay. Now let's think about another case. Let's say our case number 2. Case 2. Now our damping is not 0. Let's say our damping is now positive. So our zeta will also be positive, right? But we should select this t value such that this zeta remains 0 up to 1. Why? Because this is our under damped case, right? And we want to operate our system in this regime. Or zeta value should be less than 1, right? But it should be positive. That's why the zeta value should be between 0 to 1. So if this is the case, now let's look at this expression. Now we will have some value for zeta. Okay, we will have some value for this omega t. Also, this theta will not be exactly 90 degree or 0 degree kind of this. Okay, rather it will take some different value. Now all these terms will be present here. Expression of del delta of t. Now how can we draw the shape of this del delta of t? Okay. Let's break this into two parts. This is the exponential term and this is the sinusoidal term, the trigonometric term, right? Let's forget about this term and let's consider about this. What will be the wave shape of this term? So it will be, I am drawing it here. It will be simply sinusoidal, but there will be one phase shift, right? Let's say our theta is negative. I am drawing it considering that theta is negative. So let's say this is our theta. So it will start from here and it will be a sinusoidal curve, right? This is a sinusoidal curve. Okay. Instead of starting from here, it is starting from here. Okay. With a phase shift of theta. So this is your sin omega t plus theta. For this curve, the phase shift is theta and the frequency is omega t, right? So this is your t. Now, can you draw this term over the time? E to the power minus z zeta omega n t. What will be the wave shape? It will start, let's say, from a positive value, then it will be decaying over the time, right? Because look, this zeta is positive here. Also the omega n is positive. This term will be positive and there is minus sign. That means this will be the exponential term. Okay. Now if you multiply these two, then you will get the result, right? So after multiplication, which type of curve you will see? It will be exponential decay. It will be exponential decay. As well as there will be some sinusoidal curve, right? So it will be like this. So over the time, it will be settled down to a fixed curve, right? Have you understood this thing? Now obviously you can find the magnitude of this t from this term, from this del delta of 0 divided by root over 1 minus zeta square. This term will give you the amplitude information. Okay. So now, by looking at this, can you comment on the stability status of this system? It is a stable system, right? Now, this is for t and zeta are positive, right? Now, let's go back to this table. This is third case. Whenever our t and zeta is positive, we will get two roots on the left side of the SL. That means the system is stable. Okay. Look, what is the delta versus t response? If you continue the simulation, you will see that it is settled to a fixed curve, right? Now, if in the third case, if we take g as negative, okay, so if this g is now negative, this zeta will also be negative, right? If the zeta is negative, now here minus zeta omega n, so zeta omega n multiplication will be a negative term, minus and this minus will be plus, right? So you will see some kind of e to the power positive term. That will be the exponential growth, right? Exponential increase, not the decay. That means at that time you will get this as this, okay? And what will be the result? It will be like this. So you will see the sinusoidal curve that is going over the time, right? And this is your unstable system. That means whenever you will take your t as negative, so your zeta is also negative. So you are getting two roots at the right side of the plane. So this is the unstable system. So previously we discussed this thing from the root locations. Now we can also discuss the same thing by looking at this time domain equation of del delta of t. Same thing. Okay. Do you have any question now? Right. So by just putting these values zeta, omega n, omega t, and del delta of 0, we can just this theta we can find this del delta of t, right? Then if we just add this delta of 0 with this, we will get the delta of t. Similarly, here using this equation we can find the del omega of t. We need omega n, del delta of 0, okay? Then omega t, zeta. Then we can find this del omega of t. Then if we add the initial value of omega, then we will get the omega of t, right? And this is for zero input response, and these two equations are for zero state response. And here you can see that there is some input term here, forcing function del p, right? Del p, and there is no del delta of 0 term because this is now 0, right? Because this is zero state response means the initial condition of the state variable is 0 here. Okay. Now let's go to the textbook and let's solve this example 11.2 first. This is the statement of example 11.2, and to solve this, let's just read out this statement. A 60 Hz synchronous generator having inertia constant H equals to 9.94 megajoule per MVA. So this is your F. More specifically, this is your F now. That means your initial F. Because after some time you will see that there will be some disturbance. So whenever the disturbance occurs, your frequency, that is either omega or F, and your delta will not be fixed. It will change over the time. Okay. So that's why in the first value we are taking it as the initial value, the F. And the inertia constant value H is given. The transient reactance Hd dash equals to 0.3 per unit is connected to an infinite bus through a purely reactive circuit as shown in figure 11.7. So in the next page, a diagram is given. This is the one-line diagram for this example 11.2. So you can see this is the synchronous generator, right? And this E dash is the distribution of a synchronous generator. This is the transient internal voltage. And we have the transient reactance for the generator Hd dash. There is one transformer. This is the transformer reactance. Then we have double circuit line, and the reactance of this circuit is 0.3, right? And this system is connected to the infinite bus with a magnitude of 1 per unit. So it is said that the infinite bus at the voltage V equals to 1 per unit. Okay. So now this is our system. Now let's read out the rest of the question. Reactances are marked on the diagram on a common system basis. So the reactance values are given here. And this is a purely reactive circuit, that means there are no resistive components. Okay. The generator is delivering real power of 0.6 per unit. So this is actually your real power PE. Okay, so this is the PE, the real power delivered to this infinite bus. So this is 0.6 PE, the real power. 0.8 power factor lagging. So this is your power factor lagging 0.8. So from this you can calculate the power factor as well, right? To the infinite bus at a voltage of V equals to 1 per unit. So this is the 1 per unit. Okay. And we know that we take this infinite bus as our reference, right? That means there is some angle associated here, and that angle is actually 0 degree. You know this thing, right? So if we represent this V in the phasor form, then it will look like this. The magnitude is 1 and the angle is 0 degree. This is the phasor representation of this infinite bus voltage. Now, assume the per unit damping power coefficient G. So the value is given in per unit, that is 0.138. Consider a small disturbance of del delta, that is 10 degree, and in radian it is 0.1745. Okay, you have to consider this thing. So whenever this information is given, that the disturbance is given as del delta, that means this is actually the unforced response, right? Because you can see any del Pm term here. That means there is no forcing function. So how the system will go to the disturbance state? Using this initial condition, the del delta, right? So this is actually our del delta of 0, right? So our del delta of 0 should be non-zero to actually convert this system into the disturbance regime. Okay, so this is our del delta of 0. For example, the breakers open and then quickly close. Okay. Obtain equations describing the motion of the rotor angle and the generator frequency. So we need to find the expression of the rotor angle, that is the delta of t, and the generator frequency, that is the f of t. Okay, and we can easily say that from here actually we will get the unforced response, the zero input response, right? And for that we have to take these two equations for zero input response, these two, right? And these two equations are given here in this two equations, 11.61, 11.62. This is for delta of t, it will be the initial value of delta plus this term is actually the del delta of t, and this is the omega of t, the initial value of omega plus the del omega of t. Okay, but here we need to find the f instead of this omega, so we can replace this equation into f. How? We know that omega is twice by f, so f will be omega over twice by, right? So how we will replace this equation? We will simply replace this omega by f, and it will be equal to this will be the f naught. Okay, this f naught is given 60 Hz minus, instead of this omega n it will be fn, right? And fn will be simply omega n over twice by. Okay, then this del delta naught will be same as it is, then root over 1 minus zeta is going to be same. So e to the power minus zeta omega n, again here omega n you have to replace it to fn, and here sin omega dt should be omega t equal to ft. What will be your ft? It will be simply omega t over twice. Then we can represent and this as the f of t equation. Okay, we will see this thing, but before that we need to calculate some parameters, right? Otherwise we will not be able to find the delta of t. So we need to calculate first this delta naught. This delta naught value is not given. We have this value, right? This is the initial del delta, that is the 10 degree. This value is given, but this delta naught we do not have any information about this delta naught. So we have to calculate this value, then this zeta value, omega n, omega t, as well as this theta. Okay. So let's first calculate this delta naught. So by looking at this single line diagram, can you just tell me that can we incorporate the delta here inside any of the term for this one line diagram? Where actually this delta lies in this diagram? Yeah, this delta actually lies here associated with this angle. This angle is the delta. Can you recall? Okay, so that means if we find the value of E dash, then we need to just convert it to the phasor form, right? Then it will be the magnitude as well as some angle will be here. That angle will be the delta angle, and that will be your delta, because that will be the initial case. Okay, so like this way you can calculate this delta. Have you got the idea? Now to find this E prime voltage, first we need to draw the equivalent circuit of this. How we can do that? We have one voltage source for the synchronous generator, right? Then we have the transient reactance XD dash. Then we have the reactance for the transformer XT. Then these two parallel reactance can be drawn as a single one, right? And what will be the value of this? It will be the same value, right? So it will be 0.3 divided by 2. So simply it will be 0.15. Okay. And finally, this infinite pass. Okay. Then this should be connected, right? If we do the, if we just draw the more simplified version of it, then it will be simply E prime. Then there will be one single reactance, because we can just add these three reactants, right? Then there will be only one equivalent reactance. Then finally there will be V. Okay. So let's say this is our x. We can calculate this x. So this x calculation is given here. Look, this is your x, right? It is 0.3, 0.2, and the two parallel resistance of these two parallel thing will be plus 0.3 by 2. Okay. So if you add these three, you will get 0.65. This is x. Now you know the v, right? Now what will be the, if there is the current I flowing across this circuit, can you write the formula for E prime? Just applying the KVL. What is the formula of E prime? It will be, okay, say loudly. It will be first, it will be Ix plus V, right? But due to this x term, we need to put one J term here, right? So it will be simply V plus J. The voltage drop across this plus this voltage will be equal to this voltage. Okay. Look, this is your expression of E. Okay. Because this E prime should be calculated first. Because if we convert this E into the phasor form, then we will get this. This will be our delta node. That is our first target, right? But for this equation, we know this x, we know this v, but we do not know the I, right? So we need to calculate the I first. Okay, so we need to calculate the I. So what should be the value of I? We know that the apparent power S is actually the V I conjugate, right? So I conjugate will be S divided by V. And if we do the conjugate again in both sides, it will be the I equals to S conjugate over V conjugate. This formula, right? Now we know the V, so we can calculate the V conjugate, but we don't know the S. So how we will calculate the S value? We know the real power 0.6 and we know the power factor PF as 0.8, right? So from these two we can draw some kind of power triangle, right? If this is the theta of the power factor angle, this hypotenuse will be which power? It will be apparent power S, right? And this term will be the real power P, right? And this will be, let's say, QE. And we know that S will be simply P plus JQE, right? You know this thing, right? Okay, so we know that this P is 0.6 per unit, and we know this power factor. So if we apply the theta formula, that is the cos inverse power factor, we will see that it will be simply 36.87 degree. Now, what will be the QE? QE will be P tan theta, right? P tan theta. So that is 0.6, then tan of this theta value. Then finally you will get 0.45. Okay, this will be the value of QE. That is the 0.45. Okay. Now S will be 0.6 plus J 0.45. Then you can convert this into the phasor form. How? The magnitude will be 0.45 square plus 0.6 square. And what will be this angle? Sorry, this. What will be this angle? Tan inverse plus this term, right? 0.45 over 0.6. Okay. Then you will get this angle. You know this thing, right? So then you will get the S value. The book here the author has done it in other way. Okay. It will be difficult for you to understand this thing. You can just follow this power triangle form. Okay. And you can easily find the same thing for S. Now this is your S. So what will be the S conjugate? Simply put a minus sign in the angle. Then it will be S inverse. S conjugate divided by V conjugate. The angle is 0. That's why you can put it minus or if you put it minus or not, it will be the same. Then finally you will get this is the I. Put this I here, you will get the E prime. This is your E prime. This is the magnitude of E, and this is your delta naught, right? This is now your delta naught. So we have found this delta naught. We have found this. Now we need to calculate the other parameters like zeta, omega n, and omega t. Okay? And for that, first we need to calculate the PS or the synchronizing power coefficient. Because this is the formula for omega n, this is the formula for theta. You can see the PS is common, right? We know the F naught and H from the problem statement, but this PS is still unknown. So what is the PS formula? P max cos delta naught. Can you recall this formula? So this was the PS. PS was the slope of our power injector, right? Pmax was. What is the Pmax? This is actually the Pmax, right? This is actually the Pmax. Pmax. Then we can write it as magnitude of V prime, magnitude of V over x, right? So, good. Pmax. What is the Pmax? Magnitude of E, that is 1.35. Magnitude of G, that is simply 1, right? Over the x. X is what? 0.65. We have calculated here. X 0.65, right? So put all the values, and delta naught is 16.79. So your PS will be 1.9884. This is your PS. Now put this PS value here, and then you will get the omega n and the zeta. Okay, so this is your omega n in radian per second, and this is your zeta in per minute. Now let's apply. Okay, also we can find the omega t, that will be the omega n over 1 minus zeta square. You know the omega n and zeta, and you can find this. If this is your omega t, you can write the ft. Ft will be simply omega t, that is 6 over 12 square. So this is your ft. Also you can find the fn, that will be omega n over 12 square. Okay, and this is your second order equation. How you can write it? What was the general form? The second derivative of del delta plus, in this term it was twice zeta omega n, right? So if you multiply 2 zeta and omega n, you will get 2.62. Okay, and this term is omega n square. Okay, can you recall this general expression? It was s square plus twice zeta omega n s plus omega n square, right? This one the case. So look, this is twice zeta omega n, this is omega n square. Okay, because your omega n was 6.14. If you do the square of it, you will get 37 points. Okay, also after multiplying these three, 2 zeta and omega, you will get 2.6. Now we know all the parameters. Now we can apply this formula delta, that is delta naught plus this term. So look, this is the delta. This is your delta naught, okay, plus here this term. This is your the del delta naught of over 1 minus zeta square, right? If you calculate this term, you will get 10.234. Then e to the power minus zeta omega n. If you multiply zeta with omega n, then you will get 1.3. That's why e to the power minus 1.3. Then sin omega dt, right? What is omega d? 6. So 60 plus theta. How you will calculate this theta? It will be. Can you calculate this theta? This theta is means the theta of this. Okay, this theta. How you will calculate this theta? Simply using this formula, cos inverse theta. You can use this theta, that is the 36.87. That is the power factor. This theta means the theta that you have got from this triangle, right? That is the cos inverse theta. So if you apply that formula, you know the theta value. If you do the cos inverse of 0.2131, you will get 77.69. Okay, that is your theta. So this is your delta. Similarly, you can find the f. How? This is your f naught. So it will be simply f naught minus fn. You can find the fn from omega n. Then delta naught over root over 1 minus zeta square. Then this exponential term. Then this sine term. Okay. So sine, finally sine is okay. This is actually the analytical solution, because this, if you plot this delta versus t, you will get the exact picture of this delta. Same for this f. If you plot f versus t, you will get the exact form of f. Okay. Now we will try to plot these two. For that, you can take help of your MATLAB coding. Okay. You can just give all the values, initial value. Then finally, this will be your delta. This is your f. If you plot it, you will get this type of thing. Okay. Now just try to understand this curve. delta versus t. Okay, and what is your delta naught? 16.39, right? That is here. This is your delta naught, the initial value of delta. Now look, this is the delta of t. So at time t equals to 0, you will have your delta naught as well as there will be some value here, right? So if you add these two, you will get some large value from this delta naught. That's why you are starting from this value. Okay. Then over the time, the second term will be decaying, right? Due to this term, and at certain point it will be completely 0, right? Then you will get only delta equals to delta. That is your 16.79. That's why you are seeing that the final value of delta is actually the delta. Okay. Similarly for this f, initially you will get 60 plus this term, second term, but over the time this term will be 0 and you will get the 60 as your final value, right? So look, this is your 60. This is the f naught. But this is your f versus t naught. Okay. Obviously, you can draw this type of curve exactly with these values. Okay. From this to and from by your hand calculation. Okay. So that's why you can take help of your MATLAB. Okay. But in the example, maybe you can just plot this type of curve randomly, but you can show that okay, final value will be delta. Okay, that concept will be given. Also here you can show that okay, final value will be delta. But maybe you can be able to get all these values. Okay, about how much amount of time you will get to delta naught. That calculation will be difficult to do. Okay. So for that you can just take help of your MATLAB code. You can just try this code. Okay. Now the next example is 11.3. Here actually all the parameters value are taken from the previous example 11.2. Look, the delta naught we calculated it in the 11.2 using some steps, but here it is directly used. Okay. And here the disturbance is given by this thing. The input power is increased by a small amount. This is the input power during the okay. So now we have some forcing function. Now we will get some zero step response, right? Now for this case we have to use this set of equations for zero step response, right? And here you will see that there is no del delta of zero parameter in the equation because it is now zero. Later you will get this del t that is given as 0.2 per in the problem. Okay. And all these values are same as before. So if you place all these values, then you will see that this will be your delta and this will be your f. Okay. Because look, here the only unknown parameter was delta Tm. It is given as 0.2 per and this f naught omega n is this delta naught. Okay, this omega naught or f naught, these values are same as in example 11.2. So if you place all the values, you will get this delta and this thing. Okay, and then if you plot these two things, again you will see the same kind of phenomena here. So after certain time, you will see that your delta is settling to this value. That is the okay. Actually, here actually if you continue the okay, no, there is some other terms here. Okay, you will see that this is the delta naught, but here you will get some 5.763 minus this. Okay, so there will be actually three terms. The last term will be 0, but you will be remaining with this delta naught plus this 5.7631. So that means this 16.73 plus this will be 21 point something. That will be your final. Okay, this is due to this equation. Look, and with this equation you will get this multiplied by this one minus this. Okay, so the last term will be 0, but you will have this term plus this. That will give you the final delta of t. Okay, that means due to some okay. So what is the difference? In this case there was no forcing function. So for unforced response we get the final value of delta exactly same as the delta previous one, right? Same for f. But whenever there is some forcing function that will make your system or that will actually create this final delta as a new value. Okay, this is a new value, but also this is a stable system. because if you get the previous value as well as if you get a new value but the fixed value, then that is also the stability, right? So for this case only you are getting delta naught plus that term. Okay, what is that term? This term, okay, this term is there for 5.7 for this case. And for your f, you will see that your f will reach to f naught. Why? The equation is different here. This plus this. So this term is exponential decay, it will be 0. You will be only left with this one of 0 or f of 0. Okay, so it will be simply x of 0. Have you understood this thing? So I think this should be very much simple to you whenever you will understand the concept of these things. Okay. So with this, actually I want to conclude this slide, that is this one stability slide. And from tomorrow, inshallah, we will start a new slide that will be the large disturbance stability or transient stability. Okay. No, actually after that we will have one more slide for two machine system. Okay. If I just show you the thing. This will be our fifth slide, transient stability, and then the sixth one will be the two machine system. Okay. This thing. So from tomorrow we will start this transient stability. It is completely a large slide, okay, because we have maybe 64 or 65 pages for this slide. Okay. So it will take maybe 7 to 8 classes to complete. And the last slide, that is this two machine system, you can cover it only in one class. Okay. Because actually there is nothing. There is only four pages. Okay. Just the overview of two machine system. If the system is more than one, what will be the scenario? Give you some idea, not the exact calculations. Okay. So you can just go through this slide. It's called disturbance stability. And if you have any question in your mind, you can ask in the next class. Okay. Or anytime you can ask to me. I will try to answer. Also try to go through these examples 11.2 and 11.3. Okay. It's better that you revise this slide and these examples right now, because if you just leave it for your final exam, then before the final exam the load will be huge. Okay. And all the things, all the concepts, anything again you have to understand from this class. That will be difficult. But if you now just revise these slides, then it will be easier for you to understand.